Hi all, welcome to the course on quantum mechanics. So today I'm going to introduce a concept called wave function and its interpretation. So before going to the discussion of wave function, first I would like to just review the concept in classical physics. So if you look at the classical physics, in order to describe the system in classical physics, basically we need two quantities. So first of all, we have to know the position of particle and as well as the momentum of the particle in the same instant. So once you know the position and momentum of the particle, then we have know the complete state of the system. So the state of the system in classical physics is basically nothing but its positions and momentum. So if you have a single particle, then we need to know the position of that single particle and its momentum. If you have multi-particle system, then we need to know the position momentum of each of this particle. So if you know the position of particle of all the particle within the system, that means you have the complete knowledge about that system. So that's the one part, and that is what is called the state of the system. Now, in order to know the future state of the system, we need to know what are the forces acting on it. Okay, so by combining the information of the state of the system and as well as the forces acting on it, what are the forces, external force acting on it, then it is possible to find its future state. So for that, we have to solve the Newton's laws of motion. So by using Newton's laws, it is possible to find the future of the system. Now, not only future, we also have to find, we can also find the past of the system as well. So that means in classical physics, by knowing the state of the system and as well as the forces acting on it, and by using these two and solving the Newton's laws, it is possible to find both future and the past of the system. So that means your classical physics is completely a deterministic physics. It is everything is well known. Actually, if you know the initial things, if you know the initial state, then the entire future and entire past information is available in the present state itself. So the classical physics is completely deterministic. Now, what about in quantum mechanics? So when you're going to the classical physics to the quantum mechanics, what is the major difference? So if you're going to the quantum mechanics, the one major difference is the uncertainty principle. So this uncertainty principle forbids the complete knowledge of the position and momentum of the system simultaneously. So that means you can either know the position or we can know the momentum of the system at the same time. It is impossible to know both position and momentum at the same time. So that means due to the uncertainty principle, it is impossible to use the position and momentum as a state. So this cannot be used as a state. Then what would be the state in quantum mechanics? So the answer is wave function. So we can use a wave function to represent the state of the system. And in general, the wave function is represented by symbol psi, and it would be the function of position. It can also be function of momentum. It can also be function of time. So usually we write the psi is a function of x and t. We can also write the psi as a function of momentum and t also. But those things we will discuss later. For the time being, so just consider the psi is a function of x and t. Now, if we know the psi at present, how can we calculate the psi in future? So that is possible by solving the Schrodinger equation. So instead of the Newton's laws in quantum mechanics, we have a new equation is called Schrodinger equation, and Schrodinger equation is given as IH cross dou psi by dou t is minus h bar square by 2m dou square psi by dou x square plus v of x psi. So this is called the time dependent Schrodinger equation in one dimension, because here I have considered only the one component of position, literally x, but in we know that in general in three dimension we have three independent variables x, y, z. Okay, so those all details I'm not going to discuss now. So my focus is to discuss, to introduce what is a wave function to you. So that is why, for simplicity, I have considered the simplest situation in quantum mechanics, a one-dimension case. So in one dimension, the wave function will satisfy the Schrodinger equation, which is already given inside this square. Okay. Now, what is the meaning of psi? So in classical physics, the meaning of state is well known to us. It is position and momentum. But what is psi? The psi is in an artificial function. Now, what is its meaning? Unfortunately, there is no meaning for psi directly, and psi is interpreted for its mod square, and this interpretation is given by Born, and it is usually called the Born's interpretation. So mod psi square into dx integral a to b. So if you integrate mod psi square over a distance, then this integration will give the probability to find the particle between a and b. So that means suppose you have a wave function. So better I go for some a graphical representation. Okay, so the y-axis is mod psi of xt square, and the horizontal axis is x. So some wave function like this. So let this question is a and this question is b. So if you integrate mod psi square from a to b, then its area under the curve is a probability. Okay, so here it is not a deterministic quantity, it is a probabilistic quantity. So mod psi square is a probabilistic quantity. So that means in quantum mechanics, the probability is present in its fundamental aspect itself, because this entire quantum mechanics is based on psi, and psi itself is interpreted as a probabilistic quantity. So mod psi square is probability, or mod psi square dx is a probability, and mod psi square is called the probability density. And if you look at the dimension of mod psi square, the dimension of mod psi square should have the dimension of length inverse, because if you look at this integration, this is a probability, and the probability is a dimensionless quantity, and hence this mod psi square should have the dimension of length inverse, because dx has a dimension of length, because dx is in its length, so it is a dimension of length. So mod psi square should have a dimension inverse to length, or that means the dimension of the wave function psi should have 1 by 1 by L raised to 1 by 2, 1 by root L. Okay. Now we can go into the deep into this interpretation. Now what is this actually means? So what is the meaning of this probability? How the probability comes here? Okay, so in order to explain this probability, it is not going to work for a single system. That is the first thing we have to remember. So this interpretation will not work for a single system. So usually the probability will work if we have multiple systems. Suppose the probability to get head while tossing a coin is, we know that it is 50%, it's 0.5. But will you get this result for in a case of a single toss? This was we could not able to verify that probability using a single measurement. We need the multiple measurements and very large number of measurement. Okay, so the thing is, suppose getting the probability, okay, we can write this. So probability to get head is 0.5. So that means if you perform the tossing of a coin for around 10,000 times, then for almost 5,000 times you will get hit. That's the only thing we can say. We could not able to say what would be the output, what would be uh, uh, the result in each toss. We can only say that if you perform very large number of experiment, then you will get ahead for around 50 percentage of toss. That's the only thing we can say it. Okay, then in this case, in case of a particle, what is meant by the probability between the two persons A and B? Suppose you have some particle here, and you are going to measure the probability between A and B. So what is actually mean? So this means that you have to check the position of this particle for very large number of times. You have to perform the experiment for around 10,000 or 1 lakh times. Then we can see that between A and B there will be some different probability. That's the only thing we can say. Okay, for example, suppose integral A to B mod psi square dx. This gives 0 0.4. Okay, once again, suppose this is equal to 0 0.4. So this means if you look between A and B for 10,000 times, then almost 4,000 times the particle will be there. That's the only thing we can say. We could not able to say in a particular experiment what would be the location of particle. So if you have a particle system, okay, suppose a system I'm just showing it as a box, okay, a particle here. So in order to perform this experiment, we need the copies of the same system. We need a very large number of copies of the same system, and that is usually called an ensemble. So we need the mental copies of the same system. So if we have very large number of systems, then check, find the position of the particle in each case. Okay, so let this position is A, this position is B. Okay, suppose these are two positions A and B. I am going to check the position of the particle. So the position of the particle can be easily found out by just taking its photograph and just check whether it is between A and B. So if you take the mental copies, if you take the very large number of copies of the same system, and if you measure a very large number of times, maybe 1,000 times, so that is if you are going to measure for each set up each system simultaneously. Then almost in 40 percentage of the measurement gives a result that it is between A and B. Okay, but we could not able to say in which X what will be the output, what will be the position in each measurement. So for one particular system, for the first copy, you got between A and B. The second copy, it need not be between A and B. It can be beyond B or it can be beyond A. That it can be before A or it can be after B. That is possible. So the result of each experiment is it cannot be predictable in advance. So this kind of the probability aspect is present in quantum mechanics in its fundamental way itself. So that is why the quantum mechanics is a probabilistic physics. It is not a deterministic physics because we don't know the result. We could not able to predict the result of each measurement. We can only predict the ensemble average. If you perform very large number of experiment, what would be the average result? That is the only thing we can predict. We cannot able to predict for individual cases. So there is the main difference between when you're going to the classical physics to the quantum mechanics, and this entire thing is based on the wave function, and the wave function is hereafter is a state of the system. So all the required quantities like the position, momentum, energy, angular momentum, everything we can calculate once you know the wave function. So that's all about for now. And next, we are going to in depth about the interpretation of the results of quantum mechanics. So there are various interpretations possible. There are realistic position, orthodox position, and there is one more thing called agnostic position. So we are going to discuss these different ways of interpreting the probabilistic quantum mechanics so that we can see in the next class. See, bye.